Hi everybody, welcome to the third video. This is the second part of the Chapter 2 review. We're going to focus on implicit differentiation and related rates. Now these are topics that we didn't necessarily have you watch the videos for, so they're new topics. And if you feel like you need more examples, you can always refer back to those summer videos, and I've shared everything on Schoology there. Okay, so this first example deals with implicit differentiation. So we need to understand, well, what is an implicit equation versus an explicit equation, which is what we've been dealing with. So an explicit equation is one where we've already got it in terms of y equals, okay? So these are explicit equations, and the differentiation has been like it has been in the past, okay? Now implicit equations are equations where y is not by itself. So you can see that these two equations are identical. They're just written differently, as well as these two equations. So one is already solved for y, where one is not solved for y. The same rules apply in terms of differentiating, and we can't forget about the good old chain rule, okay? So how does differentiation or implicit differentiation work? What does it look like? Okay, so we're going to go to this first example here, all right, where we want to find dy dx given xy squared equals 10, and we're going to use implicit differentiation because the equation is not in terms of y equals, okay? So we're going to take the derivative of both sides with respect to x. That's what this WRT represents, with respect to, okay? So we take the derivative of both sides. So we're thinking product rule. So if we take the derivative of x, it's just 1, and we're left with y squared. So we're thinking of this y squared as if it's a coefficient, okay, just some number. Then that product rule, now we have to take the derivative of this part, this y squared. So we keep that x, and when we take the derivative of y squared, that 2 goes in front, times y, and we subtract the power by 1. But now we have to include dy dx, okay? So now we're taking the derivative of this y, but we want to take the derivative with respect to x, so we have to remember to include dy dx, okay? When we take the derivative of that right-hand side, the derivative of a constant is just 0. All right, so now we just clean it up. All right, now the last thing we have to do is just solve for dy dx, and we're golden. All right, so as we clean things up, we can throw this whole term over to the other side, and then we can divide by negative 2xy. And the last thing we would do is just simplify. We've got a y squared over y, so those can cancel, and we are left with our final answer. Okay, so like I said, if you feel like you need some more examples, you can always refer back to those videos from over the summer. However, the next couple examples, we're going to use implicit even further, so you might be okay. This next example, which comes from the book in that section, we want to determine the slope of the graph of 3 times the quantity x squared plus y squared squared equals 100xy at the point 3, 1. So whenever we're asked to find the slope, we need to think derivative. Okay, so it's telling us to find the derivative, dy dx. However, we should look at that equation and we should recognize that is an implicit equation, so we're going to need to use implicit differentiation. Now, if you look over on the side, I've got the answer here, but let's just prove that that is our slope. Okay, so here's what the graph looks like. Here's what the slope at that point, that tangent line would look like. Okay, so how do we get there? How do we find the slope at the point 3, 1? So like I mentioned, we need to use differentiation. Okay, so we take the derivative of both sides with respect to x. Okay, so whenever we're taking the derivative of the y piece, we have to remember that dy dx. All right, so if we're taking the derivative of this first piece, the power comes down, we're left with what's inside, and we subtract 1 from the power. However, we have to remember that chain rule. Okay, so now we have to take the derivative of what's inside. Taking the derivative of x squared, we get 2x. Taking the derivative of y squared, we get 2y, but we have to remember the dy dx. Okay? Taking the derivative of that right side, we have to remember our product rule. So if I'm taking the derivative in terms of x, all right, where y is now a constant, we just have 100y. And now I'm going to pretend that x is the constant, and we're going to take the derivative of that y term, and we get 100x, but we have to remember dy dx because we were taking the derivative of y. Okay? So now we're just going to kind of clean it up. So this is just a bunch of algebra, okay? So I'm going to try to explain it really quickly, what I did here. So I took this 3 times 2, and what I did was I distributed this piece over to this factor, okay? And that leaves us with this to be distributed to each piece. So we're going to get 12x times x squared plus y squared plus 12y times x squared plus y squared dy dx. On the right side, it stays. And now I'm just going to get all of my dy dx's over to one side. So bring this term over to the left, throw this term over to the right, and I can factor out my dy dx, okay, from this step above. And then all I have to do is divide by this this factor here to get dy dx by itself. Cleaning everything out, taking a 4 out of everything, we are left with our final answer here just for the slope, right? So this is the slope of the tangent line, okay? Now I want to go ahead and evaluate that at the point 3, 1, because that's what it asked us to do. So I have the equation of our slope. Now we just are plugging in that point 3, 1. So some notation you should be familiar with. Dy dx, this bar tells us we are evaluating dy dx at the point 3, 1. Okay, so that's that notation. You're going to see that often. Get used to it. So now I'm just plugging 3 in for x and 3 in for y into our slope equation down here. And when everything is all cleaned up, we end up with 13 over 9, okay? So the slope at the point 3, 1, at this point right here on our graph, is 13 over 9, okay? The last example deals with related rates. Okay, again, this is a new topic. If you feel you need more examples, you can always refer to the section 2.7 lectures from the summer videos that we sent out. All right, so related rates. The cross section of a 5-meter trough is an isosceles trapezoid with a 2-meter lower base, a 3-meter upper base, and an altitude of 2 meters. Water is running into the trough at a rate of 1 cubic meter per minute. How fast is the water level rising when the water is 1 meter deep? So there's a lot going on in this problem. What we need to be able to do is we need to decipher all of the information, okay? And it certainly helps to draw a diagram. And sometimes that's the hardest part, is drawing it and labeling it correctly. So the first thing I'm going to do is I'm going to look at, okay, well, what is my end goal? My end goal is how fast is the water level rising? That's what I want to know. So when I see how fast, that's telling me I want to know a rate, okay? A rate at which the water level is rising. So the water level rising is like our height. But since I want to know the rate, I'm thinking the derivative. So dH dt, that represents a rate, okay? So I kind of put that down here. What do we want? We want to know the rate, dH dt. The next thing we have to do is understand, well, what do we know? We know the water is running into the trough at a rate of 1 cubic meter per minute. Again, I see the word rate, So I'm thinking derivative. What's it the derivative of? Well, it's 1 cubic meter. So that's telling us volume. Okay, so that tells us that's dV dt. We also know, I want to know the rate at which the water is rising when the water is 1 meter deep. So that tells us H equals 1. So if we zoom in here, here's our diagram. Okay. So we are told that the cross section of a 5 meter trough. So that part is right here. Okay. 5 meter trough. What else do we know? We're told it's an isosceles trapezoid. Okay, so I kind of threw in that trapezoid with a 2 meter lower base. So that is this piece right here, the 2 meter lower base. A 3 meter upper base, that's this piece here or here. And an altitude of 2 meters. So that's this guy here, or if we're looking actually on the diagram, this red piece here. Okay. Now, if we look at it, that blue represents the water. Okay. That blue H represents the height of the water. Okay. And since I know it's an isosceles trapezoid, I can go ahead and drop these altitudes in. And I know that this piece is then going to be 2 meters. And that leaves 1/2 each for these little red pieces left over because the entire thing is 3. Okay? So this is our diagram. And it's kind of a tricky diagram to look at. All right? So kind of decipher it and see if you have any questions. So the first thing I always do is I always label what we know, okay? So we kind of already talked about this. We know that the rate at which the volume is changing, dV dt, is 1, okay? The height at which we're trying to figure out the rate at which the height is changing is 1, okay? What we want to know is dH dt when H equals 1. So the key here is, even though I know all of this information, we do not substitute until the very end, okay? Until the very, very end. All right, so let's get started. We're talking volume. We know the rate at which the volume is changing. So what we need to do is we need to talk about the volume of this trough, right? So the volume of this trough is really the area of one trapezoid, which is kind of this front face here, this guy right here, all right, times the depth, right? Because we're essentially adding all of these flat trapezoids together until we get to the depth we want. All right, so we have the area of the trapezoid times the depth of the trough. Well, area of a trapezoid, 1/2, times the quantity base 1 plus base 2 times the height, and then we have that depth. Okay, so let's go ahead and plug in. So what is the base 1? Well, base 1 is this 2 right here. So that's right here. And what is base 2? Well, base 2 is this piece here because we're talking about what is the rate of this height of the water. We're talking about the height of the water, right? So if we just label this portion X and this portion X, we know that inside here will always be 2. So that's this piece right here. But then we have to add this X plus this X to represent the water. So that's where we get this 2X from, okay? The height of the water, that's this blue H right here, okay? And the depth of the trough is 5. So now we just kind of clean it up, okay? So we get here. But the problem with the volume equaling 5/2 times the height times the quantity 4 plus 2X is we have 2 variables. We have H and we have X. We don't know what X is. So what we need to do is we need our volume in terms of H, because we do know what H is. So what we're going to do is we're going to zoom in on that red triangle, okay? We're going to zoom in on that red triangle, and I've already kind of labeled it here. So that blue represents our water, which we don't know, that's X there. We do know that this piece is 1/2 a meter. We do know that the entire altitude here is 2. We don't necessarily know the height, right? That's changing. But we can set up our similar triangles. We can set up our proportion. So this piece H compares to this whole side of the triangle. This piece X compares to that whole side of the triangle. And when we clean it up, we can solve for X in terms of H. So now we just go ahead and we substitute back into our equation. So instead of X, we now know X is really H divided by 4. So now we can clean up our volume, okay? So now we clean up our volume, and now we're going to differentiate because we want to know dH dt. So what we're going to do is we're now going to use implicit differentiation with respect to time, okay? With respect to time. Now, I don't see any t there. That's why we have to use implicit differentiation. We know, moving forward, when we take the derivative of this left side, take the derivative of v, we get dv dt, because the derivative of this is just the coefficient, 1 times dv dt, okay? Equals 10. Now we have to take the derivative of h, which is just 1, but we have to remember to include dH dt. Plus, now we take the derivative of this piece. So we have to move that power out front and subtract by 1 for that next power. And don't forget dH dt. Okay? So now we can go ahead and substitute what we know. So we labeled this in the beginning. We know dV dt is 1 and we know h is 1. So we can substitute that in for dV dt and we can substitute that in for h. Okay? And now all we have to do is solve for dH dt, cleaning everything up and getting dH dt all by itself. And don't forget to use the proper units. So we end up with the rate at which the height of the water is changing, that's the dH dt, is equal to 2/25 meters per minute. All right, so as I mentioned, these are complex problems for sure. So if you feel like you need more examples, by all means, refer back to those videos from over the summer, and always use this guideline as a nice resource as you're kind of going through. We can certainly answer questions next time we're in class. Have a good day.